Okay, so this is Chapter 6 of Dennis Wixom and Tegarden System Analysis and Design with UML 5th edition, and we're talking about behavioral modeling this time. Right, so these are basically more UML diagrams. This time we're talking about sequence and communication diagrams and behavioral state machines. The aim is to understand the process used to create them, as well as the CRUDE matrices, which we'll define later. And then you should be able to create these and understand the relationship between the behavioral models that these diagrams represent and the structural and functional models that we've talked about before. So behavioral models describe the internal behavior of the system. There's a couple of different types. There's representations of the details of the business process identified in use cases. There's interaction diagrams, sequence and communication particularly, and they show how objects collaborate to provide the functionality. There's also representations of changes in the data, which is captured by state machines. And the aim so far is to look at the dynamic view of the system, not how it's implemented. Right, so we've got use cases supported by collaborating objects, and we want to see how to depict those collaborating objects to implement the business process. It also helps us organize and define the software because we can see where the data has to go and where it has to come from. And yet again, this is an iterative process. Just because you create the diagram once doesn't mean it's going to be fixed. As you elaborate on other parts of the model, you will have to revisit the behavioral model to update it so that everything is consistent. Right? Interaction diagrams have objects and attributes and operations and the messages between them. And there's two sorts of interaction diagrams. There's sequence diagrams, which we talked briefly about before, and there's communication diagrams. The sequence diagrams emphasize the sequence of the messages exchanged between objects, and the communication diagrams emphasize the connectivity between the objects, right? So we're not that concerned with how things are sequenced. Sequence diagrams look at objects within a single use case, right? It shows the sequence of messages, and it helps sometimes in understanding real-time specifications and complex use cases. We hope to form a generic diagram that shows all scenarios for a particular use case. Sometimes we need to go to a particular scenario depending on the complexity of the sequence of the use case. Right, so here are the parts of it. Now remember, now we're talking about objects. So we're moving from the use case and analysis classes to now we still have actors. They're still pretty much the same, but they're now instances of the actors. But now instead of using classes, we have an instantiation of the class, which is an object. Connected to each actor or object is a lifeline, which shows how long or how far the sequences or the operations on the object occur. There's also an execution occurrence. I sometimes call this a lifetime. Right? It shows where the object has to exist. Then there are messages, right? You have a solid message going one way and a dashed line message going the other. These ones generally mean synchronous messages, but you can also represent asynchronous message passing. Sometimes you get a guard condition, right? An if condition on whether a message happens or not. Sometimes those guard conditions are put within context, and you put the guard condition where the word context is in the box at the bottom there. An X on a timeline indicates the object can be destroyed. Right, and here's a sample use case. Sorry, a sequence diagram. And in this particular example, there are no returns. I tend to prefer to put returns on all calls out to objects. You do want to understand, even if there is nothing coming back from the call, you need to make sure you know that. And putting the returns, for example, from a patient back to a receptionist after lookup patient, that may tell you something about what information has to go back. So when you're building sequence diagrams, set the context, identify the actors and objects that you've got to use to interact, pull down the lifeline for each object, the dash line, add the messages by drawing arrows between the appropriate objects, add execution occurrence to each object's lifeline, and then validate the sequence diagram. Compare it with the use case description with the happy flow. If it's representing a subflow as well, compare that. If it's also representing an alternate or error condition, check whether it's consistent with the use case report or the use case description. So communication diagrams have a one-to-one correspondence with sequence diagrams. If you have a sequence diagram and an appropriate case tool, you should be able to go straight to the communication diagram. They look very different, but they capture a lot of the same information. The key with communication diagrams is to show the dependencies amongst the objects, who's talking to whom. You may have heard of the law of Demeter. The law of Demeter says that they only talk to their friends, and we need to know, reduce the number of friends you have, believe it or not. Right, and here's what's on the communication diagram. Same sort of thing for an actor, same sort of thing for an object. Now we have an association, and we may have a message that's passing between two different objects or between an actor and an object. We can also have a context, a frame to show what's happening. Right, and here's an example where this is the same information as this sequence diagram, but now we're just interested in the communication lines that are drawn between the actors and between the different objects within our system. You can also see that on each of the associations between actors and actors and actors and objects are the messages that were labeled on the sequence diagram. So to build a communication diagram, set the context, identify the objects, actors and associations, lay out the diagram, add the messages and validate the model again against the sequence diagram and the use case diagram. So the third sort of UML diagram that this chapter introduces are state machines. Right? So objects change state in response to an event, and you have to capture those different states in the model. And here's an example with the patient. They can have a new patient, a current patient, or a former patient. And state machines are usually only used on complex objects. Right? The components are the states, what's the object's attributes at a given point in time, and the events, what causes the change of states. and then the transitions are the movement from one state to the other for the object. Here's, I think we've seen this before in the Somerville chapter, right? Here's the state, the initial state, the final state, an event, a transition, and again a frame or a context. So here's a sample state machine. This is for a patient. They enter the hospital, they check in, they get a diagnosis, and if they're unhealthy, they go under observation. And once they're healthy again, they get released. If they were admitted and their diagnosis is healthy anyway, they get released. And it looks like they have to be are only released if they're in hospital for more than 2 weeks. Okay, so guidelines. Use it only for complex objects. Draw the initial state in the upper left and the final state in the bottom right to start with anyway. Use simple but descriptive names for states. Look out for black holes and then a miracle occurs. Make sure you have guard conditions that are mutually exclusive. That is, there isn't a condition that allows you to take two paths from at a decision point. And ensure transitions are associated with messages and operations. Right, so you've got to set the context, identify the states, lay out the diagram, add the transitions, and yet again validate the model. Okay, we haven't talked about CRUDE analysis, and this is useful for identifying object collaborations, right? And we identify interactions between objects in 5 different ways: create, read, update, delete, or execute, right? Hence the acronym CRUDE. And we use a matrix to represent those operations or show those operations between the different objects. Right, and here's an example. Right, looks like the library actor and the student actor have an E or execute relationship between them. The library actor and the personnel office actor have a read and execute. The library actor and a book have all 5, CRUDE. And the aim is to just fill out each box in this matrix with whether the items or the objects concerned are related by one of those 5 operations. So you've got to verify and validate. You've got to make sure that actors are consistent between models, that message on sequence diagrams match associations in communication diagrams. Every message on a sequence diagram appears on the associated communication diagram. Guard conditions appear on both. Sequences of messages correspond to the top-down ordering of messages being sent. State transitions are associated with a message in a sequence diagram, and entries in a CRUDE matrix imply messages being sent. That was it. That was a relatively quick chapter, right? So we've got behavioral models, interaction diagrams, which are either sequence or communication, behavioral state machines, which show how the internal state of an object might change, and CRUDE analysis, create, read, update, delete, execute, showing the relationship between actors and objects in a matrix. And then verifying and validating, primarily ensuring things are complete and consistent between all the different diagrams and all the requirements.